Assalamualaikum warahmatullahi wabarakatuh, and good day to our fellow panels, fellow presenters, and audiences. My name is Hairun Najmi bin Kamaluddin. I am supervised by Dr. Lokman bin Abdullah from Faculty of Manufacturing Engineering, UTEM, Malacca, Malaysia. So the paper that we will be presenting today is titled Improvement of a Proportional Integral PI Controller for a Servo Pneumatic Actuator by adapting a zero-compensator placement method. Below are the contents of this presentation. As an introduction, a typical advanced controllers are very complex for a typical control system. The objective of the research is to overcome the complexity. This study is an extension from a current or previous research using a proportional integral PI controller adapted to a servo pneumatic positioning control system. The method we are applying is a theoretical method. It is one of the root locus method called zero-compensator or ideal derivative compensator. The zero-compensator method caters the improvement in the transient response characteristic of a system. In a root locus design, there are three types of design, which is pole placement, zero placement, and a mixture of zero pole placement. In our literature review, other researchers tend to focus more towards pole placement. We have listed a few of the pole placement design on a pneumatic system. One of the recent research in 2020 by Lakshmanan is an interest to us. However, the application is different to a spherical tank water level control using the method. They have a set of predefined gains for the PI controller adapting this root locus method, which is proved superior to a classical Ziegler-Nichols method. In our methodology, there are two parts, which is the first part is a system identification and the second part is the root locus design. For the system identification, we need to find the mathematical representation of the servo pneumatic system. Our system consists of a pneumatic cylinder, two pressure sensors on each side of the actuator, a carriage, a proportional valve which is connected to an air compressor, and also a position sensor integrated inside the pneumatic cylinder. All of these components are connected to our computer through the DAQ. Using the system identification toolbox in the MATLAB, we are able to extract the mathematical representation of the plans. Presented is the transfer function of the servo pneumatic system, defined as GS. GS is presented in a basic block diagram presented here. The servo pneumatic system presented GS is the main part here, controlled by the PI controller, an input, an output, and also the feedback. The previous research had a suitable gain for the PI controller using the classical Ziegler-Nichols method. The gains are presented in the table. For the root locus method, it is more towards a procedural method. Now, usually for the root locus, the method is applied to a second order, but what we have achieved here is a fourth order. Therefore, there might be an offset from the calculation to the actual response. The main objective of the design is to improve one of the transient response, which is the settling time. We want to achieve 1/3 of the current settling time. The shorter settling time means the system will reach the steady state in a shorter amount of time, which concludes to a better system performance. Here is a graph showing the transient response with the settling time. It takes for the current PI controller to the system 0.764 seconds to reach the desired output of 1. We wish to improve this by bringing it closer to 0. 0.764 seconds will be brought down closer, which means the system will reach the input faster than it is at present. The first step is to attain all the 0 poles of the current system. Now we use the MATLAB function to attain the system from the transfer function. There are 3 zeros and 4 poles from the system as displayed in the tables. The first parameter we take or extract from the transient response is the percent overshoot. Presented here is valued at 2.28%. Using the percent overshoot, we need to extract the damping ratio zeta. We use the calculation from the equation presented here to attain zeta. Percent overshoot at 2.28%, and we achieve the damping ratio zeta at 0.768. From the transfer function and also the zeta, which is the damping ratio, we generate the root locus diagram. We need to find the intersection between the zeta line or the damping ratio line to the root locus. The intersection is displayed as pole position, which is minus 0.563 plus 0.469i. From the previous dominant pole, we need to calculate the natural frequency, which is omega n. Omega n is calculated using the equation as presented. Settling time is also calculated with the parameters obtained. The settling time is 7.104. This is calculation-wise, which differs from the ones we observe from the transient response from the graph. Using the calculated settling time, we design the new parameter, which is to achieve 1/3 of the current settling time, which we now define as settling time new. So the new settling time is 1/3 of the current settling time. So we attain 2.368 seconds. From this value, we can attain the new natural frequency, which is 2.198, a different value to the current natural frequency. We need to define the new dominant pole using the new natural frequency. The new dominant pole is displayed as minus 1.689 plus 1.407i. The next step is to determine the zero-compensator angle by referencing all the zeros and poles to the new dominant pole. This is the new dominant pole. All the zeros and poles in the system are referenced to the new dominant pole, and the angles are calculated. Displayed in the table are the angles of each of the zeros and poles with reference to the new dominant pole. All of the angles are summed up and as presented in the table. From the equation, we can calculate the new angle of the zero compensator. We must note that the new coordinate of the compensator must be on the real axis and in the stable region. The angle of the zero compensator is calculated as presented. Adjustment is made based on the requirement presented earlier, which needs to be on the real axis and in the stable region. Therefore, we obtain the angle of the zero compensator as presented And calculation wise, we achieve the zero compensator location at presented, which is at minus 3.2158. The zero compensator block final implementation are as the picture shows. It is located here after the PI controller and the plants. The values are S plus 3.2158, which is the value of the zero compensator. This is the transient response of the new PI with zero compensator controller versus the older PI controller. Closing up, we see that the new PI with zero compensator performs better as it reaches the steady state faster, which concludes to a better settling time, and also with a smaller overshoots. It also reaches the peak value at a shorter amount of time compared to the PI controller. Presented in the table is the data for each of the parameter. We have rise time, percent overshoot, maximum overshoot, peak time, steady state, and also settling time. All of the values in the PI zero compensator are smaller than the PI controller, which corresponds to a better characteristic in transient response. Displayed are also the percent of improvement achieved from the zero compensator. As mentioned earlier, the approach is a second order calculation, therefore the exact result do differ from design. As specified, we'd like the design to go 1/3 of the existing PI controller for settling time. However, we have exceeded that by almost 9 times. Peak time also improves by almost 1/3 of the existing PI controller. Percent overshoot by design should remain, but it had improved further due to the calculation. There are other equations involved the tuning of the parameters obtained from damping ratio and natural frequency. We believe these parameters or calculation has effect in obtaining the transient response. One of the reasons why we achieve a better transient response is that the pole pairings have been equaled with the implementation of the zero compensator. With the PI controller, one of the pole, which is P2, is without pair, trajected to negative infinity. With the equal pairing of zero poles, the system performs better and is more stable. This is the original root locus of the PI controller. We have one pole which is trajected to negative infinity. With the introduction of zero compensator, the pole has a pairing. This is also proven by the new transfer function, where both the numerator and the denominator are both of equal same fourth order. So to conclude, we have managed to create a PI controller with a zero compensator placement, which has improved the transient response. The next step for our research is to experimentally apply the controller to the actual plant and perform the analysis. Stability performance is a norm in a control system analysis, so we must perform as well to the current controller. Our interest is to create an adaptive zero placement controller for the system. These are our references towards the study. Please leave any questions and the comments in the comment section. Thank you all to viewers, and we hope to see you again soon in the near future. Thank you.